Filengrène software tutorial for Spur gears design. The aim of this video is to help using this free software for spur gear design and machining with no complex calculation. First, download the software. The link is given in the video description. Unzip the file and double left-click on Setup for launching. From this screen, choose English for the language. This new screen is appearing. For example, pinion 20 teeth, wheel 30, module 1, pressure angle 20 degree, width 10 mm. For this, go to the top left menu and click left-click Design, and then Gear. This is for the characteristic of the gear set. So 20 teeth for the pinion, 30 for the wheel, 0 degree for X as there is no shifting, 1 mm for the module, 20 degree for the pressure angle. And these are the characteristics of the cutting rack. The foot radius is set to 0.4 mm as 0.4 module. More will be said later about this. To know the meaning of the boxes, left-click the question mark in the bottom menu. A drawing is appearing for a standard cutting rack. Here is a picture showing these two racks. For the standard cutting rack, the head radius is 0.4 module. As there is no profile shifting, x equals 0, so the definition line will be merged with the contact line being tangential to the gear PCD. All the symbols names are in the down left panel. Here is a more detailed view of these symbols used by the software with some explanations if needed. Left-click the 2D in the bottom box in the bottom menu to get the dimension again. Beside the gear definition panel is the geometry panel with other results. Actual pressure angle alpha t, here 20 degree as there is no shifting. The center distance 25 mm, and also interferences if occur. The contact ratio, here alpha, but the usual name is epsilon alpha, must be more than 1.3 for good running. Not good if less, orange box in this case, but if under 1, the box will be red, as the gear set can't run correctly in this case. Specific sliding to equalize the wear between pinion and wheel. Not very good here, so orange box. Here is a more detailed view of these symbols used by the software with some explanations if needed. If the mouse passes on the box, an information is given in the download panel. Left-click the 2D box to get the results again. Go to the top left menu and left-click Metrology. The control values are appearing. The span measurement is the most convenient for us, but there are also the vernier caliper and the pin gauges values. The span measure is the easier way for controlling a spur gear with a standard caliper or a dish micrometer. Go to the top left menu and click the Help box to get some information about the boxes and the display. I give you some information about the display menu using the mouse. Use the wheel for zooming. Click the wheel and move the drawing across the screen. Double-click the wheel to get thicker lines. Right-click the wheel, right-click and move to see the gear meshing. It's also possible to go to 3D view, not of much use for spur gears, but could be interesting for other gears. Go back to the geometry panel, the 2D and geometry panel, but click now on strength. You must have some knowledge in the strength of material subject to use this part of the software. Fill the boxes. Young's modulus, Poisson's ratio, for the gears materials and pinion torque, here set to 5 Newton meter. Root stresses appearing for the pinion, for the wheel, the contact pressure, and the static error due to deformation. More details now. Click Design and now Pinion. We had chosen 0.4 as root tooth radius for the pinion, but as this tooth radius is the envelope of the rack radius due to the cutting motion, this actual rack radius is 0.317. So modify to 0.4, being the standard one, and calculation. Make the same thing for the wheel, design, wheel, 0.4, calculation. Go back to the design gear, and you can see that a new value is appearing for the stress, being less than the previously one due to a greater radius in between the teeth. Far more things can be done in the pinion or wheel menu. These are refinements for professional gears, as topping, protuberance, profile correction, and width correction. Not detailed here. If you want to know more, go to the video about the software possibilities. A link is given in the description. These modifications can only be obtained from CNC machining, 3D printing, or bespoke gear cutters. We are only speaking about the gears that can be cut with standard cutters of the generation types, hops for example. If you click on the question mark in the bottom menu, when you are in the pinion or wheel menu, the cutting rack is appearing for the topping and protuberance definition. For us, HF0 equals HT0 and HA0 equals HP0, as we don't want these refinements. Now some examples for other practical situations. First example, removing the undercut. We want to make a 10-teeth pinion meshing with a 100-teeth wheel in a gear quadrant used for helical milling. Module 1.5, pressure angle 20 degree. It's necessary to remove the undercut of the pinion as Z less than 17 by profile shifting. The minimum value being X equals 17 less Z divided by 17. This equals 0.411. More about this in my video about involute gears. Choice here, X equals 0.45. As no strength calculation is needed, the tooth radius can be set to 0.6 as 0.4 module. So go to Design, Gear, fill all the change geometry, and fill all the information. 10 teeth for a pinion, 100 for the wheel, 1.5 millimeter for the module, and so the radius, foot radius 0.6 for the two gears. And now we have the result, and we can see that there is an interference problem, because I have not modified the shifting to 0.45. Now there is no interference, and we can move the gear, double click the wheel for thicker lines. The important reasons for us are the pinion's head diameter for machining the blank, and the span measurement, 7.331 say millimeter for the span measurement across two teeth. Now some play with the software. If we change the X value, you can see that the specific sliding is not very good. If we change to 0.45, here the sliding situation is better, and the teeth are sharper, of course. So this could be a good information. But now we are playing with the software, increasing to 0.8 for here many problems are appearing. A very sharp and worse than sharp tooth, so interferences, and the radius, the contact ratio is not good, and the sliding situation are not good. So it's worth letting the shifting to 0.45. Second example, adjustment of the center distance. Have a look at the Ferguson paradox and watch the video for the full description. A link is given in this video description. The common center distance is given by the first gear set, Z equals 30, and module 1 for the two gears, so the center distance is 30. The center distance is the same for the second gear set, but now one gear is 29 teeth, so a profile shifting is necessary to get the same working plane. For this, go to the gear design menu. Here we are, and fill all the boxes. 30 millimeter, 29, but erase the X values. Module 1, the tooth radius 0.4, as already seen. And the actual center distance is 29.5, but we want 30 millimeter. So double click the box and write 30. Automatically the X boxes are filled with the right values for X. They are optimized for the best sliding conditions. All the necessary values can be obtained for gear cutting as already seen, so the head diameter for the wheels, and in the metrology, the span measurement for the pinion or for the wheel. The same routine can be used for the last gear set, using 30 to 31 teeth, but now, of course, the shifting will be negative. Now some more information for 3D printing. In the design menu, go to pinion, and now take the 3D display. It's possible to add a chamfer in the chamfer box. Give a value 0.5 millimeter, and the chamfer is appearing. It's also possible to change the bore in the CG box. Set a number, the greater the number, the smaller the bore. It's also possible to modify the bottom radius of the tooth. Here it's 0.4 millimeter for the rack. Double click, and automatically the maximum radius is appearing, this giving the maximum strength for the tooth.